I want to thank my co-authors and collaborators of the Weather and Chaos group at the University of Maryland. And sorry. Sorry.
Those buttons.
Yeah, sorry. I am nervous. Sorry. I haven't learned anything from yesterday. Yeah. So, Lorenz introduced, chaos is the dominant characteristic of numerical weather prediction, and Lorenz in 1963 introduced the concept of chaos in meteorology. As Professor Velasco said, Poincaré actually introduced it in science. York in 75 coined the name chaos, which perhaps it's not the best name in the world. So, even with a perfect model, showed Lorenz, and the perfect initial conditions, we cannot forecast beyond 2 weeks. So this is the so-called butterfly effect. But when Lorenz in 1963 did this amazing work, this was only of academic interest, very much academic interest, because the forecasts were useless essentially beyond a day or two. Now we exploit chaos with ensemble forecasts and routinely produce skillful forecasts beyond a week. And actually, the El Niño coupled ocean atmosphere instabilities are allowing 1 year forecast of climate anomalies. And so I'm going to talk a lot about breathing, which is a method that is very, very simple, and it allows you to explore and fight chaos, exploit it. And I'm going to show how undergraduate interns found that with breathing they could easily predict the Lorenz regime changes under duration. I will show that we plan to use it to predict solar wind storms. And this weather chaos research led to the University of Maryland local ensemble transform Kalman filter, LETKF, that I'm going to talk about tomorrow, which is a wonderful method for data assimilation. So the basic central theorem of chaos, if we want to say so, is that unstable systems have finite predictability, so that's chaos, and stable systems are infinitely predictable. And here it's there are two solutions, or one is the truth and one is a forecast, and the initial conditions are almost perfect but not quite. And whenever there is an instability, the small differences grow, and eventually they become completely different. And by contrast, if you have a stable dynamical system, it has periodic solutions. So even if you start from a bad initial condition, you will be able to predict it. So this is an example which is from actually 2003, which shows how instead of having forecasts that go 1 or 2 days like it used to be when I was young, we can do, this is an example of an 8-day forecast and the verification. This is what actually happened, and this is the flow, the pressure or geopotential isolines of the 8-day forecast. And it's really amazing because essentially in weather maps you have highs and lows, and essentially every high and low is essentially in the right place, except for this one. And but where the prediction predicts a cutoff low, and that there was only a trough there, and that has a large impact on the winds. So the winds in the prediction are towards the continent and away from it towards the ocean in reality. And this is this was associated, it's interesting because it was associated with a very Santa Ana strong type of winds. So the fact that the winds were in this direction is what allowed these fires to persist, whereas if it had been as in the forecast, it would have stopped with moist air. So I'm going to start with a Lorentz model, which is a simple chaotic model that he published in 1963, and it has, as most of you have seen this, it has two regimes, and the transition between them is chaotic. And as Lorentz discovered and stated, if we introduce an infinitesimal perturbation in the initial conditions, the forecast soon loses all skill. As Professor Velasco said in the introduction, the extreme sensitivity to the initial conditions, as I have to copy the name of that novel that described it so well. So we have two solutions here, one in blue and one in red, and they have basically 1 bit difference, and they stay together, and then they start visibly separating, and then immediately they completely become completely different. And I had the good luck of listening to talk of Lorentz in a workshop when he was 89, and a year or two before he died, and he defined chaos when the present determines the future. So you have a model that tells you from the present the future, but the approximate present does not approximately determine the future. It's a very beautiful, clear definition. And indeed, that's what happens. And there is a very famous figure created by Palmer in 2002, where he took the attractor of the Lorentz model, which is given by all the points every few number of steps. And he took all the points that were within a ball and followed them. And if he chose the initial ball here, it was stable and they remained together. If it was here, it was less stable, and if he chose the initial conditions here, it became clearly unstable. And so the point, one point is that errors with unstable initial conditions, which have growing errors of the day, which is a phrase that I introduced in Japan when that is now widely used, errors of the day, growing errors of the day. So with unstable initial conditions, the growing errors of the day grow much faster. So the basic idea is, how can we tell whether the errors grow or not? So we had an 8-week project for undergraduate women to convince them to study science in 2002, and they were undergraduates and they didn't know programming or certainly. So I had to find an easy problem. So I asked them, play with a famous Lorentz model. We gave them their model and explore its predictability using this breeding method that Zoltan Toth and myself created at NCEP. It's a very simple method to study the growth of errors. So we told them, imagine that you are a forecaster living in the Lorentz attractor. So everybody living in the attractor knows that there are two weather regimes, the warm regime and the cold regime. But what the public needs to know is when will the change of regimes take place and how long they are going to last. So can you find the forecasting rule to alert the public that there is an imminent change of regime and hopefully how long it will last? So I'm going to explain what breeding is. And breeding is simply running the nonlinear model a second time from perturbed initial conditions and rescaling every so often, for example, for the atmosphere every 6 hours or every day. So we have an unperturbed control forecast, which here is a straight line, but it changes with time. And then we start with an initial random perturbations, and initially random perturbations don't grow much because, as Professor Velasco said, there are many directions that are stable, so they don't grow much. But when you get to this, you rescale the whole solution by the same growth factor, so that the amplitude here is the same as here. And then it grows faster because it's more dominated by the growing errors. And it grows faster and faster until it sort of reaches the asymptotic size. And this difference between the perturbed and the control is what we call bread vectors. That we call them bread vectors, vectores criados, because we grow them in order to develop in order to pick up the naturally fastest growing solutions. So actually, by construction, it's very obvious that bread vectors are very related to the leading local Lyapunov vectors, and actually it's like bread vectors are like a generalization of finite time, finite amplitude Lyapunov vectors. So we can compute also the growth rate. The growth rate is the size of at the end of the interval divided by the initial, which is constant. And you take the logarithm and divide by the time of this growth, and this is like an estimation of the exponential Lyapunov growth. So these 4 summer interns computed the growth rate, and they painted it. So red means large bread vector growth, and blue means that perturbations decay. And this, I actually did this, and by mistake, I also got the X solution here, or the white solution. So you can see that the large growth occurs at the bottom of the attractor, as Palmer had shown, and this is just with a single bread vector integration. It's totally trivial to show. So in another way to look at it, when the bread vector growth is high, which means the local Lyapunov vector growth is high, it's red. If yellow, it's medium, green is low growth, and blue means that the perturbations decay. So with a single breeding cycle, we can estimate the stability of the whole attractor. And so we thought this was very nice and easy. So this looked very promising. So I asked the interns to paint x of t, the value of x of t with the bread vector growth. And when I saw the result, it almost made me faint. So here it is. You can see very clearly that the fast growth rate precedes a change of regime in the previous orbit. So the last orbit before a regime change, you have a very large growth rate. There is a change, and so on. And actually, you can see there are some mistakes. For example, here there was one period of large growth rate, but it didn't happen. But generally, it's very robust. And the other thing that you can see is that if the growth rate doesn't last long, then there is a change of regime, but the next regime is short. Whereas when you have a lot of growth rate, the next regime is long. So we did create forecasting rules for the Lorentz model. One is regime change. The presence of red stars, fast red vector growth, indicates that the next orbit will be the last one in the present regime. And regime duration. If there are 1 or 2 red stars, the next regime will be short. Several red stars, the next regime will be long-lasting. And actually, Jim Hansen, one of the co-authors, showed it to Lorentz himself, and he said, wow, this is very interesting, which is amazing because yeah, I was expecting him to say, I knew that this. I did it in 1964. But so these are very robust rules, and I don't know if you can see them, but for very long cases, if you have lots of red stars, the next regime is long. If you have one, the next regime is short, and so on. So we score them, and they are correct in more than 95% of the time. So if you were a forecaster,
you seem to have some false alarms.
Do you
have any failures to predict?
Any? About 5% are not correct.
No, you say 95%. I mean,
both rules.
No, but there are two kinds of errors.
Yeah, false alarm and
failures to predict.
Failure to predict.
So do you have
both? We have both. Yeah. In the paper we put the
just from the figures that you showed, it seemed to be mostly failures to. Mostly false alarms.
Because they are easier to detect. Yeah, with the eye. Yeah. The next point is we started working with Professor Surya Sharma, who is an astronomer at the University of Maryland, and 2 students, and Kayo Ide, and we are trying to apply these ideas to a physical system for which we don't know the model. And I'll show that at least for the Lorentz model, we don't need to know the model to predict regime change. We suppose that the question would be, suppose that you live in the Lorentz model attractor and you only measure X. Can you predict regime change from only measuring X, not knowing the whole model? So for many systems, we only know time series for a few variables. We can predict regime changes in the Lorentz model without knowing the dynamical model. So I'll show you that we use time delay embedding method to reconstruct the phase space. We only know the time series of X, so we don't know Y or Z in the Lorentz models every 8 steps. So we use, since we don't have a model, we cannot do regular breathing. So what we do is nearest neighbor breathing. So we do breathing, and then for the solution, we find the closest neighbor to the point and the one that has the right direction. So after rescaling, we choose the closest neighbor in the same the same direction. And so we reconstructed the Lorentz model with time delay embedding, and that's this attractor. And here is the original breathing that I showed before, standard breathing in the Lorentz model. And here is if instead of doing the standard breathing, we choose the nearest neighbor from the attractor because we have a long history. And then if we do embedding, and in embedding we only have the X observation of the first variable, and then every 7 steps we choose another value and we call it variable 2, and then after 7 steps another variable, another value and call it variable 3, and then repeat and repeat. and this is what we get. So nearest neighbor breeding gives results similar to the regular breeding with about 0.98 correlation in the rescale growth. And in the embedded case, we do nearest neighbor breeding without any knowledge of the model. We just have the X time series. So
but you do have to have a pretty long time series.
yeah.
As Lorenz himself pointed out in 1969.
Yeah, yeah. But my colleague Surya Sharma was very interested in applying this to space weather, for which there are time series that are very, very much detailed and long.
I know, sir.
Great, great. So you should have known that. Okay, so here we test whether we can predict the regime change. So the original Lorenz model and the embedded model that knows nothing at all about the Lorenz model, just a single time series, give us essentially the same accuracy, almost the same accuracy in predicting regime changes. Here this is the standard breeding, this is the nearest neighbor breeding for the Lorenz model, and this is the embedded model using only X of t. And they all have similar skill in prediction, and this one has more separated values in the high growth rate because of the embedding that takes every 7 values. But so this is very, very encouraging, and Kayo, Ide, and Erin have done also use the LETKF and data assimilation in the embedded space, and the results are just incredibly good. So we plan to apply this methodology to solar wind data assimilation, where there are time series that sort of oscillate like this, and then all of a sudden you have a big episode, and so we try to see if we can predict that. Maybe yes, maybe not. So breeding is a simple generalization of Lyapunov vectors for finite time, finite amplitude. You simply run the model twice, take the difference and rescale, and you can apply it to any dynamical system for which you have a model. Breeding in the Lorenz model gives accurate forecasting rule for the chaotic change of regime and duration that surprised Lorenz himself and can be applied to real-time series. So now we are going to apply the same ideas to fight chaos in the full forecast models that have dimensions of 10 or 100 million rather than dimension 3. I'm going to show you results in the atmosphere, in the ocean, in Mars, and in coupled systems. And we can use breeding. This is perhaps the most exciting part. We can use breeding to understand the physical mechanisms of the instabilities that create chaos. And I have to thank once again Michael, because when I showed him the results, he said, you should explain the physics, do the energy equation. He was right. Yeah, we did that, and it's very exciting. So a major tool to fight chaos is ensemble forecasting, and maybe I'd like to show, sorry. I have a book that I would like to donate to the library of CIMAT if you don't have it. It's called Atmospheric Modeling, Data Assimilation and Predictability, and it talks of in detail, not for super genius, but for the rest of us, explains how we do things. So and yeah. So we developed breeding to create initial conditions that had growing errors like the real errors in data assimilation. So at ENSEP we introduced breeding, ensemble common filter. Actually we we beat the European Center by a week in implementing it. So suppose what is an ensemble? Suppose that we have an X here that gives you the data assimilation best estimate of the initial conditions. So you integrate and you get a control forecast, and then you put the perturbation, let's say a positive and a negative perturbation, and you get these two. And then from these three forecasts, you can take the average forecast. And then a few days later, you know what actually happened, so you have the verifying truth. And it is one of the amazing things about ensemble forecasting is that the average forecast is much closer. It tends to zero out or reduce the errors in the solution, and it's almost always much closer to the truth than the original forecast. So this is a good ensemble, but this is a bad ensemble in principle because we have the control forecast in green, the positive and the negative perturbation, and the average, and then comes the truth, and it's not a plausible member of the ensemble. Obviously, this is wrong. So we used to think this is a failure of the system of the ensemble, but actually it is actually full of information, because what this is saying is our system has a bug, so to speak, that doesn't contain the mechanisms that make the truth be different, and we have to find it. And so this is an example of as I showed, sorry, I don't know what we, yeah, this is the cover of my book. It shows a very predictable 6-day forecast with errors of the day in this region, and what it shows is about 20 ensemble forecast members, but we only show one line of for each forecast. So each line is a different forecast, and these are called spaghetti plots. So
Can you just say for the non-meteorologist what the spaghettis are?
Yeah.
I mean,
you want to say?
No.
These are one. It's 500 millibar height. So and it shows one line, one contour line of pressure at that level, one contour for each system, and generally the pressure is lower at the poles and higher at the higher latitude, so that when this is, for example, this is extended from the poles to the tropics, that's a center of low pressure. So when this is a very historic forecast, because when the human forecasters saw this 6-day forecast, and they saw it 1 day later because we didn't have enough computer time, they immediately said, wow, this is forecasting a blizzard, a snowstorm, a very strong snowstorm in the eastern coast. And they had seen many cases of a 6-day forecast or a 9-day forecast or a 3-day forecast predicting snowstorms, and then the following day the model would change its mind and predict no storm. So the fact that they were all predicting a snowstorm made them have the courage of, for the first time in history, make a 5-day forecast of a snowstorm, which actually happened because the black line is what the verification. So it shows a stable prediction of a very strong weather event, and also a very uncertain prediction here. This has errors of the day, and it looks like it's a complete mess. Actually, let me show the next slide, because it compares the 6-day forecast, which is here, with the 4-day forecast for the same day, so started 2 days later. for the same day, and I don't know if you can see, but the characteristics are identical, except that the amplitudes are a little bit smaller because it's a 2-day later forecast. So this area of uncertainty is completely identified, and it's identical essentially to the one after 6 days. So this tells us that this area of lack of predictability due to errors of the day is a property of the verifying flow, is a property of the atmosphere at the verification time, because the verification time is the same in these two figures. So at the errors of the day are instabilities of the background flow, which is the flow of the atmosphere or the model. And at the same verification time, the forecast uncertainties have the same shape. So this is very, very powerful. And this is another example of spaghetti plots where there are it's much shorter forecast, but it also predicts a storm, and the center of the storm changes with the solution. So there is a lot of uncertainty of where the storm will be located, but the uncertainty is amazing because it lies on a one-dimensional space, not on a million-dimensional space. So this simplicity, which is that locally the instabilities have low dimensionality, inspired the local ensemble transform Kalman filter of Ott et al. And Hunt et al. 2007. So this is an example of a 5-day forecast. I don't know if you can see it. There is a lot of instability here. And even the chaotic ones have local low dimensionality, which makes possible to do ensemble Kalman filter with 50 ensemble members, not a million ensemble members, with good results. And after 15 days, Lorentz has won. So we just have chaos. So let's, in the rest of the talk, we look at chaos in coupled fast, slow systems. The atmosphere has fast, very fast instabilities, which are convective clouds, which basically have 20 minutes of lifetime, and slow instabilities like baroclinic or which are the weather instabilities in mid-latitudes and other instabilities. So the coupled ocean atmosphere system has even slower instabilities. El Niño southern oscillation has periods of 3 to 7 years, and I'm honored to have in the audience George Philander, who is one of the leading lights in understanding and El Niño, and he even created the word, the expression La Niña, which is widely used now by everybody. So in order to predict this phenomena, we need to isolate fast and slow instabilities. We cannot use, if you the instabilities that have 20 minutes or 3 or 4 days of lifetime or 7 years of lifetime cannot be predicted if we have to isolate fast and slow instability. So if we can predict ENSO, we can predict climate anomalies a year or more in advance. Maybe this is too strong more, but in principle, I would think that when we have closer to perfect models, we should, and do the initial conditions right, we should predict the El Niño anomalies maybe half of the period, so maybe 2 years in advance, someday. So breathing is a finite amplitude, finite time instability of the system. It's like Lyapunov vectors, but it's done with a non-linear system. So in a coupled system, we have fast and slow modes, and a linear approach like singular or Lyapunov vector, we only capture the fast modes. That I will show you that. if you have a method like Lyapunov vectors and it has fast and slow instabilities, it will, or singular vectors, only the fast instabilities will be, because they are faster than the slow instabilities. So can we do breeding of the slow modes? So we developed a coupled slow and fast model. So we added a time delay, a time scale here, which was 10, and coupled the fast equations with the slow equations, and we call this the ocean and this the atmosphere. But then we added a third one, which is tropical, extratropical atmosphere. So basically, the model is like this. We have a tropical ocean that's quite slow. It has a time scale 10 times longer, and it's very strongly coupled with a tropical atmosphere. And then we put an extratropical atmosphere, which is weakly coupled with a tropical atmosphere, and which introduces extra noise. And this shows the time evolution of the X component, and it's we fiddle around with the equations until we found this beautiful equation, which has what we call El Niño, and then normal years and El Niño, and the El Niño happens every 3 to 7 years. Yeah, it's a Lorentz model, but the main thing that we did was add a slow down and then a coupling with a fast atmosphere.
I'm confused. I thought that Lorentz equation, the very basic physics, was convection.
Yeah, but this was done.
It's not a model. It's what people in dynamical systems call a metaphor.
Or a toy model. It doesn't mean to represent.
It's not really how you model the ocean, but you are trying to model this business of slow and fast scales. That's
coupled,
all.
yeah.
Okay.
Thank you.
I like metaphor better.
Yeah. Well, this total model has 9 equations and not a million for the atmosphere and a million for the ocean. So we want to see the dynamics and want to see whether breeding can separate the fast instabilities that are in the extratropical atmosphere and the slow instabilities of the coupled tropical system. And actually, I'm not going to discuss this, but we showed that with a short rescaling interval of 5 steps and small amplitudes, we capture perfectly the fast modes. And with long rescaling intervals with 50 steps and larger amplitudes, we capture perfectly the ENSO modes. But by contrast, linear approaches like Lyapunov vectors or singular vectors, always, even when you try to capture the slow mode by increasing the interval, it always gives you the fastest possible instability. So they don't work in this. So in examples of breeding in a coupled ocean atmosphere with coupled instabilities, we can do breeding to isolate the fast or the slow modes. For the slow modes, we have to choose a slow variable and the long interval. This identifies the coupled instabilities. And I'm going to show a few examples. So this was done by Chikamoto et al. And they were trying to find the Madden-Julian instabilities by choosing an appropriate rescaling up amplitude. And this shows the power of breeding, because their model has this very slowly moving Madden-Julian oscillations, and this shows the shape of the instabilities that give rise to them. And when they took a relatively large amplitude compared to the climatological oscillations, they did get the Bredt vector solution in the upper levels and in the lower levels. If they took an amplitude which was 10 times smaller, like we found when we first started doing breeding, they basically what they capture is the convective instabilities of the individual clouds. And finding the shape of the errors in the El Niño forecast to improve data assimilation. So Bredt vectors are the differences between the control run and the perturbed run. And should the Bredt vectors show the shape of the growing errors? And this was our basic motivation. When we do data assimilation, we make a forecast error and the forecast errors grow. And then we have observations and we make it closer to the truth, and then forecast and make it closer to the truth. So it's kind of breeding. And so we assume, we thought that the Bredt vectors, by doing this growing and reduction, rescaling and growing and rescaling, would show the shape of the growing errors. And I'm going to show you a very striking example. So this is an example from Shuqi Yang's thesis. It's a vertical cross-section at the equator for Bredt vectors which are shown with contours, and 1 month forecast errors which are shown with colors. And this was done at NASA, with a NASA system. And on the left is the Niño 3 index. In 97, 98, there was a very strong El Niño, which is at the maximum here, the mature stage, and then it decays and it became La Niña. And this is before it started, and then while it's developing and during the maximum, and we can see in colors again the forecast errors, at least as seen by the analysis, by the operational system at NASA. They made a 1 month forecast from the analysis and then compared with the next analysis, which is based on observations. And we can see the colors represent the errors in the 1 month forecast, and the contours, the Bredt vectors. And we can see that before the 97 El Niño, the Bredt vectors and the errors are located in the Western Pacific strongly and near the coastal region, and then they evolve, both the Bredt vectors and the actual errors. They evolve under the around the thermocline, and then they surface at the maximum. They are still here, and after the event, the errors are located mostly in Eastern Pacific. And the fact that these Bredt vectors that don't know anything about the future errors, except that they want to grow them as fast as possible like the errors do, they capture this so well is a very strong indication that indeed breeding gives you the errors. And this is another example that shows in the equatorial Pacific there is something that sometimes occurs, sometimes it doesn't, which are called tropical instability waves. And this is the equator, and this is like North America and South America. And the colors are the basic solution, and it shows that there are these waves with cold temperature, and the contours are the Bredt vectors, which are clearly trying to make these instabilities grow even more and even break. So Michael Gill said, look at the energy of the Bredt vectors to explain why. So Hoffman et al. Did an experiment, a student, Matt Hoffman, did an experiment using an ocean model, MOM2, which, driven by the reanalysis 1 winds. And sometimes it develops tropical instabilities with 10 days, and there are very few extratropical instabilities that appear. And I want to emphasize that we didn't know anything about the instabilities of the ocean. We just run it, and the bread vectors don't need to be encouraged to appear. They appear because they show the instabilities by themselves. So this is if we rescale with 10 days. But if we rescale with 30 days instead, then these become weaker, and there are much stronger instabilities in the extratropicals, and this is an example that there is a poster of the South Pacific convergence zone, very strong, and I'm not sure what this instability is, but they are physical instabilities that are brought up by the bread vectors during the assimilation. And there is a little bit of this. The amplitude is much smaller because their period is much shorter than 30 days. So in this case, we have both tropical instabilities, bread vectors, and extratropical instabilities. So I want to focus on this. And Matt Hoffman computed the bread vector kinetic energy equation, which can be computed exactly because both the control and the perturbed solutions satisfy the model equation. So one can get an equation for the evolution of the kinetic energy for the bread vectors. And it has horizontal fluxes and other terms, and then it has conversion from potential energy to kinetic energy. This term says if heavy parcels of water go down and light parcels of water go up, then the potential energy gets reduced and it gets converted in kinetic energy. And it is interesting that it shows that the tropical instabilities are dominated by potential energy going to kinetic energy, which is the normal situation. But in this case, for the South Atlantic convergence zone, it's negative. So it means that kinetic energy is being converted to potential energy. So we thought this must be wrong, but then we realized that the South Atlantic convergence zone is driven by the winds. So the winds create currents, and the currents create potential energy. So that will explain that potential energy is converted in kinetic energy. I mean, kinetic energy in potential energy, which is, I've never seen it before elsewhere. So, and now I'm going to just give you a very quick show of how do the bread vectors look in Mars. So this was done by Graybush et al., and he made a very beautiful analysis. Mars is very has a baroclinically unstable atmosphere, but it's not unstable all the time. So this is the winter in the northern hemisphere, and it has a front with a jet in the upper levels. And green is where the bread vectors are growing, and as I'll go over a season. Now they are starting to grow here and here. Okay, so I guess this is my last slide. Chaos is not random, it's generated by physical instabilities. So breathing is a simple and powerful method to find the growth and shape of the instabilities. These instabilities also dominate the forecast errors, and we can use their shape to improve data assimilation. And ensemble command filter, which is very strongly related to breeding, is the ultimate method to explore and beat chaos through data assimilation. In the chaotic Lorentz model, the growth of breed vector predicts regime changes and how long they will last. Breeding can be applied to a time series even without knowing the model. Nonlinear methods like breeding and ensemble command filter can take advantage of the saturation of fast weather noise and isolate the slower instabilities. Breed vectors predict well the evolution of slow coupled forecast errors for El Niño, and breed vectors help explain the physical origin of ocean and Mars instabilities. Ensembles of breed vectors improve the seasonal and triennial forecast skill, especially during the spring barrier, which I didn't show. Thank you very much.